Hello, everyone. Thank you for spending your valuable time here with us today. And thank you for your interest in learning more about graph accelerated machine learning with TigerGraph Machine Learning Workbench or ML Workbench. So today we have the following items on the agenda. We will begin our session with an introduction to a user's journey on graph data science. What kind of questions can graph analytic or graph machine learning can answer? And then we will do introduction on our latest product, which is called ML Workbench. What is it about? Who is it for? And why it is impactful in terms of helping our customers to advance along the journey of graph data science, which would enable a leapfrog in business impact. We will then go over some of the key features and functionalities our product offers. We will then have my colleague here, Nikita, to walk us through a real-life example to showcase how to apply graph data science in a fraud detection use case. Nikita will show us some very interesting benchmark results comparing three models developed by conventional machine learning approach versus graph-enhanced model, which contains unique graphy features, and finally, a graph-native learning model with graph neural network. We will leave a few minutes to talk about how to get started with ML Workbench for both on-prem and our on-cloud offering, and where to find resources you may need to kickstart your graph machine learning journey. So what is graph data science and what does it mean to your business? I want to showcase a wide range of application here. So graph data science is the use of analytical techniques to uncover insights from connected data. And there are many types of graph analytical techniques. So in this chart below, we want to categorize these techniques into the following categories. So going from left to right, ranging from less complex to a more complex graph algorithm, one can write a simple n-hop queries or graph traversal queries to find out things like what is the shortest path from point A to point B. And one can also do graph analytics or analytics, such as finding the most influential person in the network. In this case, the most influential doctor in the healthcare network, for example, by running PageRank. As we move forward to the right side of the chart, we are moving from a more descriptive analysis to a more predictive type of analysis using ML approach. So a data science can choose to run a graph algorithm or a set of graph algorithms to create or generate features and feed them into a traditional machine learning model to formulate a better prediction, or to use embedding to do some similarity measures. And last but not the least, graph native learning. This is the most cutting edge ML technique in the field at the moment. And GNNs have been proven its success across many domains, outperforming other cutting edge traditional machine learning models. So as you can see here, the more complex the analytical technique is, the more complex business questions we can answer. So now with this graph data science journey in mind, let's talk about how our TigerGraph product offerings can help guide our users to advance forward in this journey. Now to start with, we need the right data platform. So TigerGraph database being that secure distributed database running on an MPP or a massive parallel process engine that can handle terabytes of data. So this will be the foundation to store our connected data. And this provides the right platform for our customers. Now with your data store with TigerGraph, next we will need an expressive query language to describe a business question. So this is a query language for our user. Likely you will be able to pick up GSQL very quickly due to its similarity to SQL. Now, GSQL is a Turing-complete query language, which means that it has the same expressive power as any other high-level programming language, such as C++, for example. And this is extremely important because with GSQL, you can write a very complicated algorithm or query to perform your graph data science. And then now we also have the graph data science library. You can think of it as your dictionary of graph algorithm you can choose to mine or to generate insights. Currently, we have about 55 plus graph algorithm published. They are open source and customizable, which means you can see the logic behind each of our algorithm, and you also have the freedom to further rewrite it or customize it, based on your business need. Now, because these algorithms are, just like any GSQL queries, these algorithms are implemented using GSQL, and this means they are running extremely fast, leveraging our MPP engine. And they can be further optimized by hardware accelerated FPGAs. Now, finally, the topic of this session, TigerGraph ML Workbench, which would enable our users to develop supervised machine learning models such as GNN to do node predictions or link predictions. ML Workbench is fully integrated with TigerGraph database, which means you can directly leverage TigerGraph as a data source, generate and to generate features and plug it into your, plug the machine learning workbench into your existing ML pipeline and infra as a on-prem solution. And also coming up in July, you can also leverage our on-cloud offering solution, which would offer end-to-end ML as a service from development, training, tuning to deployment in one spot. Okay. Now, in the previous slide, I briefly mentioned about graph-enhanced machine learning model with graphy features. So I want to double dip on this topic. So what are these graphy features, right? How can they be generated? So inside the graph data science library, right, as earlier I mentioned, we have 55 plus algorithms, and we categorize into these 8 categories. So you can find algorithms like shortest path, PageRank, PageRank for doing centrality, Louvain for community detection, and so on. So, and then the green categories here are the newly added in the past few months. They are more towards machine learning. You can run topological link predictions. You can generate embeddings by running FastRP or Node2Vec, or you can do frequent pattern mining. So all these algorithms can produce additional attributes or features for your model to learn from. And again, these algorithms are running inside our database, leveraging our MPP engine, so they are performant. And again, you can run this algorithm individually, or you can stack them up to generate more complex features to solve your business use case. So next, I want to briefly touch on graph neural network, if you are not already familiar with it. So the reason GNN tends to outperform other traditional machine learning methods on a connected data set is because not only can it learn from attributes of a node or an edge, but GNN also learns directly on a graph's connectivity and aggregate and capture these useful information from a node's neighbor and their neighbors of neighbors. GNN can be used to do vertex level prediction. So example, fraud detection or risk, predicting a risk score. So these are the type of node prediction or vertex prediction applications. It can also be used for edge level predictions, like building a recommendation engine for products or for your contents. And the next is the graph level prediction. An application could be predicting whether a protein structure, given this whole graph or protein structure, is this structure toxic or not? So these are some sample applications where GNN can excel. So now that we have established the usefulness of graph machine learning, and I want to talk about the challenges today, and that is, before we introduce ML Workbench. We have seen research paper published by big companies like Facebook, Pinterest, Amazon, but a lot of times many companies do not have a big research group like these companies. So we want to, democratize graph machine learning for other companies. So building graph ML models a high bar to entry. It requires one to be knowledgeable across several domains like deep learning, graph data science, and being able to write a good graph query. Now, building a toy example or doing academic research versus building an enterprise level application also presents different challenges when your graph is at the terabyte size, with hundreds of millions of edges. Now, there's also a lack of integrated solution on the market today that connects graph database with different with different ML infrastructure. So that means I need to do a lot of manual or mundane tasks related to data engineering, data processing, and manipulation. So all these challenges translate to a longer R&D cycle and slower speed to delivery. So now we design ML Workbench having these challenges in mind, and we want to build a product that can help democratize graph machine learning development for everybody. So TigerGraph ML Workbench is a Jupyter-based Python development framework. It is designed for everyday data scientists use. ML Workbench is prepackaged with Python libraries to build and built-in functions for graph data processing, manipulation, subgraph sampling, and data loading, so that our users can focus on implementation using Python, which they are already familiar with, and they don't need to worry about learning a new programming language or graph query language. ML Workbench is also compatible with the most popular ML frameworks such as PyTorch Geometric, DGL, and TensorFlow. We offer both as an on-cloud, a fully managed ML service from development all the way to deployment, or it can be deployed as an on-prem solution to work with your existing ML infrastructure hosted on, say, SageMaker, Vertex AI, and Azure. So just to summarize, the key benefits of using ML Workbench, our ultimate goal is to bring value to your business. With GNN being that most cutting edge ML technology, we want our users to have bigger business impact with their graph data stored in TigerGraph. With ML Workbench on cloud, there's also no upfront cost. You will only pay for what you use. We want to ensure your data science team to have an easy development experience. So we do the heavy lifting behind the scene to provide the most optimal graph traversal queries and built-in functions for data preparation, so that your data science team can focus on the model development at the Python level. ML Workbench is designed to work together with your existing ML pipeline and infrastructure, so that minimal effort is needed to get started or to get integrated. You can just simply pip install our Python libraries and you will be ready to code your graph ML models. And finally, because ML Workbench is tightly integrated with TigerGraph database, this means our user will get the same benefit when it comes to database performance and scalability. So next, we will have Nikita here to do an interesting demo for us by applying graph machine learning techniques to solve a fraud detection problem. So Nikita, take us away.
Thanks, Andrew, for your presentation. Hello, everyone. My name is Nikita Iserson, and I'm Senior ML and AI Architect in TigerGraph. And today I will present you how to detect fraudulent transactions and accounts using a TigerGraph-powered graph neural network. Graph neural networks are very important in fraud detection because they provide unsupervised and even contrastive learning capabilities, which could be used in presence of really very difficult challenges in fraud detection, like label scarcity and label fidelity. More than that, on top of the graph that you have in the graph database, you could calculate different features using graph algorithms, which Andrew has presented, and these features could enrich your training data with the contextual information. At the same time, you could use graph embeddings and graph data models for the large-scale similarity search, and you could transform graph embeddings into additional features, which you could use later in your downstream machine learning pipelines. Last but not least, you could also use graph data models and graph neural networks for the explainable AI, because it shows how all the data, how all the root causes and consequences are connected. Let me present solution overview as well, so you could see it from the left to the right. On the left, we have the set of our data sources, and it consists of blockchain transactions. In this demo, we use Ethereum blockchain transactions, of course, not the full Ethereum, but just a particular block range. And on top of that, we have the set of blacklisted wallets or phishing or fraudulent wallets, which we took from the data set itself, and we collected them over the open source databases like CryptoScamDB, EtherScamDB, and etc. We loaded this data into the graph model in TigerGraph database, and we calculated several features on top of that. We could start from the simple features like aggregated features like send amount, minimum send amount from wallet, received amount, minimum received amount from wallet. We calculated also very simple graph features like in degree and out degree, which is in this case number of incoming or outgoing transactions. And we also calculated the page rank feature, which shows us the overall value of this node in terms of the whole network from the perspective of how connected this node and how much influence it could spread across the whole network. So we connected to TigerGraph database using the TigerGraph Machine Learning Workbench, which is Jupyter Hub-based environment where you could train your graph neural networks using your favorite frameworks like PyTorch, DGL, or TensorFlow. And at this point of time, let me share my screen. So I will start briefly with the TigerGraph integrated development environment, Graph Studio. In this environment, you could see your graph data model. It's pretty simple. We have the account node, which has the features which we already discussed, like is it the fraudulent node or not? What is the in degree and out degree? What are the sent amount from this wallet? What are the received amount by this wallet? We have also attributes which shows us the training, test, and validation split, which are actually generated automatically by TigerGraph Machine Learning Workbench. And we have the edge between accounts, which actually represent transaction in this case. And it has also a couple of attributes like amount of transaction and like timestamp of transaction. Let me jump quickly to the Explore Graph UI and show you that in TigerGraph, we could actually do exploratory data analysis, and we could basically take a look at the different visualization and on the different patterns for the fraudulent nodes and legitimate nodes. We could explore neighborhood for the fraudulent nodes over one hop neighborhood, over two hop neighborhood, and we could even calculate the shortest path between legitimate node and fraudulent node to show how many fraudulent nodes are in the neighborhood of the particular node. What is important, we will show how graph neural network could automatically extract such patterns from the data set and show it to you in an explanatory manner. As Andrew has already mentioned, in TigerGraph, it's quite easy to write queries using the JSQL, and I would like to show how you could do that to calculate the amount, aggregated amounts, which I mentioned, like send amount and received amount. You see, it takes us just 20 lines of code to calculate it. The same is with degrees. So for every vertex, we just traverse from one vertex to another, and we calculate the simple counts, and then we just save the values on the attribute of the account node. Last but not least, we are able to calculate features based on the graph algorithms, which we have more than 55 algorithms implemented natively inside the database. So in this case, we have the PageRank algorithm, which is a little bit more complicated than previous ones, but also take not more than 100 lines to implement. And you could modify the code. You could implement some temporal dependencies, some particular weight dependencies which you need. So all our algorithms are actually open source. As you can see, this particular demo, I'm actually using TigerGraph Cloud system, which is free, and you could register your TigerGraph Cloud system and actually try TigerGraph Machine Learning Workbench on top of that. But let me switch actually to TigerGraph Machine Learning Workbench. And as you could see, the demo is prepared in Jupyter Notebook. So let me go from the top to the bottom. The first step is to connect to the TigerGraph database, and you see how easy it is with the TigerGraph Machine Learning Workbench. You have just to provide the host name, the graph name, the username, and the password, and then you do the token authentication. If you would like to calculate and to enrich your nodes or accounts of wallets with additional features, you could just run installed query inside a TigerGraph. For example, if you would like to add degree features or add amount features, that's pretty simple. We could also check what is the statistics for the positive labels and for the negative labels. For example, in this particular data set, we have approximately 1,200 fraudulent accounts, and we have around 30,000 legitimate accounts, wallets. So this will be our basis for the training. And actually, this particular data could be even split into the training and validation part, and all the necessary attributes will be automatically generated inside TigerGraph. So you do it with the vertex splitter function. After that, it could also take a look how easy it is to apply a particular featureizer to our data. So in this case, we could use the PageRank algorithm to add additional features. So we are using the featureizer of the type PageRank, and we supply it with the parameters like vertex type, account, edge type, transaction, and we would like this algorithm to output top k vertices after the calculation. They will be actually persisted in the database as well as a features for our accounts. So you could see what are the PageRank values calculated for the top 5 accounts or wallets. The next step is quite important. So we need to add hyperparameters for neighbor sampler and for graph neural network itself. And it worth mentioning that in TigerGraph Machine Learning Workbench, you could also train your graph neural network in a mini batch fashion. So if you have really large data set, you don't need to load it to the memory of your Jupyter notebook at once. You could just define the batch size, which is 5,000 in this case, and you could define number of neighbors to expand from every seed vertex. And at the same time, you could control how many hops of traversal to do for this particular batch constructions. And train neighbor loader and the validation neighbor loader, and it's quite easy with the TigerGraph Machine Learning Workbench neighbor loader function. With this function, you could just define what are your input features like in degree, out degree, send amount, page rank, what we already discussed. You should define what is your target label. You should define what is your training or validation split and what is the attribute responsible for the split. You could define what is your output format. In this case, we will output the data directly in PyTorch geometric format. So you don't need to change anything if you're already using graph neural network with PyTorch geometric. You need just to put your graph inside a TigerGraph and connect to it via TigerGraph Machine Learning Workbench. We have the same definition of the neighbor loader for the validation part. And as I've mentioned already, we defined hyperparameters with respect to the neighborhood sampling. So we have the batch size, number of neighbors to expand for every seed vertex, and we have number of hops. Let's go to the most interesting part where we need to define graph convolutional network architecture. And we are doing this using PyTorch geometric. We have 7 input channels because we have basically 7 input features. We have hidden dimension defined in hyperparameters. It's 128. We have 2 layers, which is usually enough for graph convolutional networks. And we have basically 2 output channels, which is used for the decision if it's fraud or not fraud. We have some regularization parameters like dropout or optimal braid damage, how it's called. and we have the learning rate, and we have the weight decay or regularization penalty. This is the usual steps that you need to do, and we have optimizer like Adam. So that's a very usual steps that you need to define the architecture and the training parameters for the usual neural network or for the graph neural network. But let's switch to the training loop. In this case, that's quite a lot of code, but it's quite usual if you have seen it already. We iterate over our training loader and we update our gradients. So we assign some class weight for the less frequent class, and we calculate cross entropy or binary cross entropy or negative log likelihood loss, and we update our gradients. We calculate several metrics on top of our training and validation batches. In this case, we decided to track and use metrics which are used in production and used in the real life projects for the fraud detection, which are area under receiver operating characteristic curve, area under precision recall curve, and precision and recall. So as I've said, we do it for the training part and for validation part, and we get the following output, which actually reflects how the model is training. But not to show you lots of text, we actually integrated our TigerGraph Machine Learning Workbench with the tensor board, which is the graphical user interface to track different machine learning experiments and their performance. In the tensor board, you could see many experiments which we had according to different dates and according to the train or validation part. And as far as you can see, if we take a look at the area under receiver operating characteristic curve, that we have the big jump at the start, which is the kind of learning curve of the graph neural network, and then it's reaching a plateau, which is around 98, where the area under receiving operating characteristic curve is around 98%. And you could see it's quite high across the different runs and the training and validation parts of the data set. We see the same performance with the area, very similar performance with the area and the precision recall curve. So we see it starting learning very quickly and then reaching a plateau, and the area under precision recall curve is reaching around 80%. Which is quite good, and that's quite a usual picture. That's how the training performance of the graph neural network should look like. You have a big jump at the start, and then it's reaching a plateau because we've extracted all the useful necessary information from the data set, from the labels, from the graph structure. So it usually happens after several epochs, and we see we are doing that quite successful here. The same, but overall the same, but opposite picture we could see with the binary cross entropy loss, which we are trying to minimize, and we see that's decreasing. So we have decreasing loss pattern, which is quite good. It seems that we were able to learn quite efficiently. So it means our neural network has actually converged. So you could train lots of different models, and you could compare them between each other with different hyperparameters and settings. But let me switch back to our Jupyter notebook and show you that we actually augmented our model training with explainability model, which is available in PyTorch Geometric. So it's quite useful because for the correctly predicted nodes, which are rosy ones in this picture, we could actually provide the explainability subgraph, which shows why these particular nodes were classified as fraudulent. And in this particular case, you see that exactly these particular nodes, which we have as the correctly predicted to be phishing fraud, they have lots of incoming connections. They have lots of connections to legitimate nodes, and it actually highlights how the phishing fraud use case works. So there are some nodes which accumulate the money, accumulate the Ethereum coins from the different legitimate nodes. But if we would like to have the more detailed explainability behind that, we could actually show local feature importance. It's not that easy to show global feature importance with graph neural networks because of the nonlinear decision surface, but we could show local explanation. So for every fraudulent node, we could see what are the important features which are contributed across the neighborhood, which contributed to the particular prediction, which is correct in this case. And we see that in one particular case, we have out degree and send amount and page rank as the most important features. And in other cases, we have in degree and receive amount as the most important features. So this contextual information, which is added during the feature engineering phase, is very important, as well as the structural information which we could see on the particular subgraph. At this point, that's the end of my demo, and I would like to hand it over to Andrew. Thank you very much for listening, and speak to you later.
All right, thank you, Nikita, for the great demo. I hope this session has been useful for the audience here today. Last but not the least, I do want to highlight our ecosystem support for ML Workbench. We are not just offering a product to our users, but we're also interested in working with you to explore what are the potentials of applying GNNs to different domains. Internally, we are always working to create more demos or cooking recipes to build GNNs for different types of applications. We also have a form of dev community support. We also welcome anyone to bring their discussions to our Discord channel. So please also don't forget to check out our YouTube channel. We make a new YouTube series showing several tutorial videos like this one on setting up ML Workbench and different ways of creating various GNN applications. So if you're interested in getting started with ML Workbench, we have different paths to onboard. The easiest approach is to use our on-cloud offering coming up in July. There is no upfront cost, no setup required. You can simply create a notebook instance and connect to TigerGraph database and start developing your GNNs. We also have Sandbox image, which would contain both the TigerGraph database, the free version of TigerGraph database, and ML Workbench bundled together for on-prem setup with your own computer or your own infrastructure, with everything pre-configured and sample data preloaded so that you can get started right away. If you already have an ML infrastructure, say with SageMaker or Azure or Vertex AI, you can actually download our Jupyter plugin as well. So thanks again. We are looking forward to see what exciting projects you are building with ML Workbench. Thank you, everyone.